Welcome back.
Hello.
Hello. All right, so we've done a lot of work in the past couple of sessions with triangles, with similar triangles, and tons of proportion stuff. One fraction equals one fraction. Cross, multiply, solve. And you guys are like, I got this. So we're going to make it one step more complicated, because that's what we love to do in these classes, is take something easy and just keep adding more stuff to it. But we're going to start at the beginning of that more complicated with the term geometric mean. Have you heard the word mean before?
Yes.
Yes, so when it refers to people, it means not nice. Yeah, not nice. But when it refers to numbers, it means
Not nice.
not nice. Yeah, the average. It means the average. It means add all the stuff up, divide by however many things that you had, and you're done. But we have, that's like I think it's an algebraic mean. This one is a geometric mean. It is slightly different. To calculate the geometric mean, you will not add up a bunch of stuff and then divide by however many things that you had. What you are going to do is take the positive square root of the product of whatever you get when you multiply two numbers together. You take the square root of that, the positive square root. And I'm going to lean on that for a second, because square roots actually have two answers. Yeah, I'm about to clear up. Okay. If I said, what's the square root of 4? You would say?
2.
But there's another answer to that.
Negative 2.
-2. Because -2 times -2 is also 4. And so square roots have two answers. They have the positive version, which is the first thing that you all said, and then the second version, which is the negative. And so what the geometric mean is asking for is that first one, the positive one. Okay? In Algebra 2, pre-calculus, calculus, what's coming up for you next in the next couple years, you're going to have to be dealing with the fact that we've got this positive and negative thing going on. But right now for geometric mean, just the positive version. Okay? All right. Here's your formula for the geometric mean. If we let x be the geometric mean, then you can calculate it by taking two numbers. This is the geometric mean for two numbers, by the way. And you're going to multiply these together. I have a feeling that the geometric mean of more than two numbers is slightly different. But I don't know, I haven't researched it yet. But for two numbers, and that's all we're going to work with in this class, for two numbers and only two numbers, this is the formula that you will use. And it comes from, dun dun dun, this proportion. Oh, I totally used the wrong color. It comes from that proportion, right? Because if you were to cross multiply and solve this, you would get a times b equals x squared. And how do you get rid of square powers?
Square root.
You take a square root. And so x would be equal to the square root of
X.
a times b.
Are we going to need to know that equation right there?
This one?
Yeah.
No, because this is your basic proportion cross multiply solve thing. The one that you want to play with is this one. Okay? So let's do a bunch of examples with that. And then it'll be easy.
Is the star a multiplication?
Yes. All right. We have 9 problems, of which we are definitely doing 4 and 9. You guys get to pick the other 2 to 4 questions you want to do.
8 and 5.
Any others?
7.
7. That sounds about.
We're definitely doing 4, for sure.
I mean, 6.
6.
Okay.
That feels okay?
Yeah.
All right. We're going to start at, excuse me. We're going to start at number 5, work our way to 8, then go back to 4, and then jump to 9. All right, here we go. So the direction states, find the geometric mean between each pair of numbers. One of the numbers will be our A, and the other number will be our B, because our formula says that the geometric mean is equal to whatever we get when we take the square root of A times B. Okay, so I'm going to substitute. This one's A, this one's B, and now I need to find that. Pre-AP class, No decimals, unless the directions specifically state decimals are okay. The directions did not state decimals are okay, so they are not. You must reduce this manually and simplify it with all of our simplification of radical techniques. Okay. Well, I could think of this as the square root of 12 times the square root of 20, which could work. Okay, let's try that. Okay, so let's do that. Let's think of this as the square root of 12 times the square root of 20. All right, now, the square root of 12. What are the factor pairs of 12, where one of those two numbers is a perfect square?
6 times 2.
6 times 2, does 6 have a perfect square root?
3 times 4.
Hang on, we're going to do,
Oh, sorry.
we're going to deal with the 6 times 2 first. Does 6 have a perfect whole number square root? Does 2 have a whole number square root?
No.
No, so 6 times 2 won't help. You guys had suggested 3 times 4.
Yeah, that's
4 has a perfect square root of 2, and so we're going to think of 12 as 4 times 3. We're going to do the same thing to 20. Factor pairs of 20 where one of them is a perfect square. 5 times 4, because 4 has a whole number square root. Excuse me. Each of those square root of 4s I'm going to replace with the square root of 4, which is, I remember we're doing geometric means, so we're going to think positive 2, not the negative 2. Okay. So each of those square root 4s I'm changing into a 2. I say as I start to write the square root. All right, now all the 2's I can lump together. That's 2 times 2. 2 times 2 is?
4.
And now I have the square root of 3 times the square root of 5. I can write that as a single square root, and I multiply the radicands, the stuff inside. 3 times 5 is? And that's my final reduced answer.
Oh.
Pre-APs, I need to see this, the formula, your substitution, and then whatever work you need to show to get to this final simplified answer.
So basically everything.
Basically everything. But I mean, in here, I took some short, I went the kind of the long way to show everything that was happening. And there's some that could probably think through things without needing to show so much. And so if you don't need to show so much in here, I'm okay with that, as long as I see enough to know kind of what's going on in your head. Okay? Okay. We're going to repeat. 1 is A, 1 is B. It doesn't matter which one is A and which one is B. Okay. Gonna substitute. Which one is A for you?
4.
4 is A. All right, right on. Okay, you have 2 ways to go about this. You can simplify it from here the way we did the first one, or you could multiply 4 times 25 together. She wants to multiply them. All right, let's do it. And the square root of 100 is?
10.
Did you want to see it the other way?
No, ma'am, this is more easy.
You're like, no, please. This is easy. At the end of the day, pick the one that will work best for you in the moment. Okay? We okay with this?
Yes.
All right, shall we do 7?
And then we can do 4.
And then we're going to do, do you want to skip 8 or do you want to do 8?
We can skip 8. 'Cause
We can skip 8 because you're feeling comfortable with it? Okay, then we'll do 7 and then we'll jump up to 4. All right, so 7, our formula, our substitution. All right, and now we have a decision to make. Are we going to multiply them together or simplify from here?
I think let's simplify.
I'd like to simplify from here as well because I can see that the square root of 16 has a whole number. It's 4. And then I just have to deal with the 30 later. I don't have to try to figure out what 16 times 30 is and then try to find a factor pair of 16 times 30 where one of them is a perfect square. The factors are already shown for me. Right? I've already got that done. Okay, so I'm going to simplify from here. Square root of 16 times the square root of 30. Square root of 16 is?
4.
4, so right now I have 4 times the square root of 30. And now I'm going to try to think through 30. Does 30 have factor pairs where one of them is a whole number square root?
No.
Three,
Uh,
no.
No. No. None.
Yeah. And did you hear that conversation you guys were having with yourselves in your head? And some of you were verbalizing. You're going, okay, 2 times. No, that doesn't work. And then 3 times. Someone went, oh, 3. 3 times 10. But 3 doesn't. And 10. Okay, so no. And then that's the kinds of conversations you want to have. Okay. And if you're worried about showing work or things, writing down you keeping track of that conversation is a perfect and legitimate way to show this is what I did. All right, so since we can't find any factor pairs of 30 that have whole number square roots, we're going to box that one in and call it done. All right, you asked me to skip number 8, so we're going to jump up to number 4. Number 4, same as all of them. X, the geometric mean, equals the square root of a times b. One of them is a, one of them is b. So this is 1/2 times 2. What is 1/2 times 2?
1.
1. What's the square root of 1?
1.
And you're done.
But I thought that would be much harder.
Right? Me too. Yeah, no, it's number 9 that's going to break our heads a little bit.
I thought this was the hard one.
Spoiler alert.
Okay.
It's because of how the fractions worked out. You know what I mean?
So let's go to number 9.
Yeah. All right.
It's gonna be
Get ready. All right, so I'm going to super color code this one because we could get lost easily. Okay, so one of these is A and one of these is B. Here's my formula. Okay, now here's my substitution. I'm going to try to write this as neatly as I can with my color coding so that we can see what we're doing. Okay, do I need to zoom in? I'm writing small because there's a lot. Can you see it? Okay. All right. When we have fractions that we are multiplying, always multiply straight across. That means numerator times numerator. Denominator times denominator. All right, so I'm going to end up with some sort of fraction. What's my numerator? And my denominator? All right, and so now I have that my answer is the square root of 1/8. Oh, God. What? Okay, anytime you have a radical that has a fraction inside of it, you can always exchange it for a fraction made up of radicals. What and why would that looks way more complicated, right? But wait, go with me on this. Okay, so now I have this. But look at that numerator. What's the square root of 1?
1.
What's the square root of 8? I don't know, it's just the square root of 8 right now. Again, because we're not dealing with decimals. Already a little more simple than it was before. Just a little. Just a little bit, except you're not allowed to have radicals in the denominator of a fraction. You can have them in the numerator. Numerator is fine.
Aren't you supposed to multiply by something?
Yeah, we got to do stuff. All right, here's what we got to do. I'm going to move this off the side. We'll bring this back in a second. You're welcome to grab an extra sheet of paper if there's not enough room for us to write what we need to write on here. And you don't have that much space on the back, and I'm sorry. So I'll give you guys a couple seconds to grab an extra sheet of paper if you want it.
Oh, you multiply by itself, right?
Almost.
By half of itself?
Wait. I love that you guys are guessing. I love it.
Because I remember doing that.
Yeah, you remember doing this. You may have seen this a little bit in Algebra 1. You're definitely going to deal with this in Algebra 2, which is why
Rationalization.
I want to take a moment. Denominator. I want to take a moment to talk about this so that way, 1, it refreshes you from Algebra 1, and 2, if you don't remember because you were asleep that day, that was me, you have it a little bit so that when you hit Algebra 2, hopefully this makes a little bit more sense. So we're going to do something called rationalizing the denominator. It gets rid of the radical in one part of the fraction, either in the numerator or in the denominator, okay? Depending on what you're trying to target. We're targeting the denominator, but if you were targeting the numerator, you would do the same thing, but you would look at it from the numerator's point of view. All right, so here is the fraction that we want to rationalize. What we want to do is multiply by a fancy looking 1. That's all rationalization asks you to do, is multiply by 1.
Okay.
Okay? And the reason why we're multiplying by 1 is because we don't want to change the quantity that that fraction represents. We don't want to change its value. And if I multiply by anything other than 1, I'm going to change its value.
Right.
But if I multiply by 1, it doesn't change the value, it just changes the way it looks. So I'm going to change it by a fancy looking 1, some sort of fraction 1, where the top number and the bottom numbers are the same.
Oh, like 2, 2?
Like a 2 over 2, 3 over 3. But we want a specific number, and I love that she picked 8, so that it completes the radical and makes it a perfect square. In order to multiply radicals, I have to have a radical, so I'm going to put radical both top and bottom. And now I'm going to think, what do I need to multiply to 8 to fill it up to make it 8 squared?
8.
8. So that's what I'm going to put in the radicand. And now when I multiply straight across, I'm going to end up with, and I'm going to write it vertically here. When I multiply these straight across, I'm going to get square root of 8 over
Square root of 164.
the square root of
Wait, no,
64.
64 or 8 squared. I'm going to write this as 8 squared for now because I want to show you that this will work for any value or letters or anything that you happen to have in there, okay? Anytime you have a square root over something that's gotten squared, the squared and the square root cancel each other out, and so that denominator is just 8.
Yep.
Well, what happened to the numerator?
It's the same.
It's right here.
Did we change it?
Nope,
No.
it stays exactly the same.
Because the numerator can have the radical, but not the denominator.
Right, numerator can have the radical, denominator cannot.
So
So is
denominator.
it gonna work like that all the time? So basically, you're just gonna put the
In here,
so basically all that happens.
you're just
put the-
repeating itself. If it's a square root, yes. If you don't have a square root, because in Algebra 2 you'll be dealing with like the third root or the fourth root, you're going to have to figure out how many you need to fill in there in order to get this number right here, the exponent, to be the same as the little number you'll see out here, the index.
So for now, it's just gonna be.
For now, it's going to be 2 because this is a square root. And with that name square, that word square in it, it makes the index 2. So when the index and the exponent match, they cancel each other out and you're left with just that single thing. Great questions. Thank you. All right. We're not quite done because we need to simplify the square root of 8 to see if we can cancel out anything in the numerator. So just like we have done with this, we're going to think of factor pairs of 8, where one of the factor pairs is a whole, has a whole number square root. 4 times 2, because the square root of 4 is, and so this fraction then turns into 2 times square root of 2 divided by 8. And can I reduce 2 over 8? Yes, and it becomes 1 over 4, and so my final fraction is the square root of 2 over 4. And so for number 9, the geometric mean is the square root of 2 over 4.
Whoa!
I got confused.
Yeah,
when
I
she
got
started simplifying.
confused.
Okay, so from here
Yeah.
on. All right, so I wanted to simplify this radical. So I needed to think of factor pairs of this number 8, where one of those factors has a whole number square root. And you guys told me 4 and 2, because the square root of 4 is 2, which is what I wrote right here.
So 2 over 4.
And 2 over 8 is 1 over 4.
And then
You guys were right at that moment of, oh, that's really cool. And so you, yeah.
okay.
All right, good. Let's come up and let's do that theorem. There's a theorem on the front page. It doesn't have a name. I don't know why this theorem doesn't have a name. All my other theorems had names. Here's the theorem for you that does stuff. Here's what it says. It says, if, oh, come on, pen. Okay, if the altitude is drawn to the hypotenuse of a right triangle. Okay, I'm going to pause there so that we can remind ourselves what the altitude and the hypotenuse was. The altitude goes from one of the corners toward a side and intersects at a right angle, and the hypotenuse is the side that's directly across from the right angle. So you're going to be looking at a right triangle, the big one, and you're going to see a line that comes from the right angle, goes toward another side, and creates another right angle. Okay? It ends up creating these two right triangles, and these two right triangles that get created are going to be similar to each other. And to the original triangle. With all the similarity properties thereof.
I forgot and get confused with the
Okay.
hypotenuses.
Okay, so with the hypotenuse, and I'm going to draw it here from this triangle, find the right angle. Now take your pen and put it on the corner of the box and pretend you have a ray gun and shoot it away from the box. Pew! This side that you ran into is the hypotenuse. Always. Every right triangle. For the rest of eternity. Yes. Always. And then it will always have been the hypotenuse since the beginning of time. Math is the only subject that can do that for you. It's really cool that way. Okay, so let's flip the page and let's work on the setups, okay? And I really want to spend a lot of time working on the setups of these because there's like 3 triangles and they're all on top of each other, and it's really easy to get lost as to which triangle is which and what side corresponds to what side. So, who knows the story of Goldilocks and the 3 bears?
Everyone.
Yeah.
Who has not heard of the story of Goldilocks and the 3 bears? Okay, good. Just as a quick recap.
Hello,
Yes.
Steve Gabrielle, please show believe in.
Thank you. All right. That's okay. It's all right. Okay, so basically this little girl named Goldilocks goes into a house where there's 3 bears, baby bear, mama bear, papa bear. The baby bear has the smallest things, mama bear has the medium things, and papa bear has the big things. We're going to draw the 3 triangles, the little tiny baby bear triangle, the medium mama bear triangle, and then the big one, the papa bear triangle. Okay? That's how you're going to hear me refer to them. Ready? Okay, so let's draw those, and I'm going to draw them separately. So there's the baby bear, there's the mama bear, and there's the papa bear triangle. Okay, so here's one side of each of those triangles. All of those are the corresponding sides. These are all the corresponding sides. And these are all corresponding sides. Okay, so I've drawn the small triangle that gets created. I've drawn the medium triangle that gets created. And I've drawn the big triangle that gets, well, that we started with. And now I've got to figure out what information goes on what side. And I've already pre-color coded the corresponding sides for all 3 of these triangles. All right, I'm going to start with the little one. Because on the little one, it's really easy to find the short side and the mama bear side and the papa bear hypotenuse side. All right, and now I'm going to fill in my baby bear triangle. So the pink side is 1, the blue side is X, and I have no information on the green side, so I'm going to skip it and move on to the next one. Okay, we're going to repeat again here in the mama bear triangle. Looking at just the mama bear triangle, this one is the short side, this one is the medium side, this one is the hypotenuse side. All right, X and 3 and no information. Repeat again, but for the big triangle. And I'm going to color on the outside. That way you're able to see which pieces go with which. Okay, so if I'm looking at this big triangle, this is the shorter side. This is the medium side. And this is my hypotenuse.
Do you have anything to check that, or you just have to look by eye?
You have to look kind of by eye. If you've got enough measurements that you can confirm it. But otherwise, at this point, just your best guess. Because the ones that look like they're going to be about the same, because they're all similar, the ones that look like they're going to be about the same size are going to be the ones that are corresponding. All right, so it looks like the Papa Bear triangle is totally not going to help us out here because we don't have enough information. But if I look at the Baby Bear triangle and the Mama Bear triangle, I notice that their corresponding sides have information. And so I can write this as a proportion. You can either write blue over blue equals pink over pink. Or you could write blue over pink equals blue over pink. And that's how I'm going to write it today. So blue over pink equals blue over pink. And now I can cross multiply and solve, and we're back to the realm of what's really comfortable and really familiar.
3 equals x squared.
Which means x equals the square root of 3. But look at my directions.
Nearest 10.
Ha! Calculator.
Oh,
And now you don't have to simplify the radicals, because it says to the nearest 10. So as soon as you get something with a radical, you just stick it in the calculator.
1.7.
And you 1.7, and then boom, you're done. What I'd like to see pre-APs is at the very least some sort of way for you to keep track of sides, whether you draw it out, whether you use colors, it doesn't matter to me, whatever works for you. And then your proportions set up, you solving it down for x, the final, whatever, the starting radical, and then you can do your thing, okay? So just some documentation of how you're keeping track of your sides. So that way, if I notice that there's something that's going to go wrong for you, I can step in to help. Okay? All right. We're doing great on time. We've got 20 full minutes. We are definitely going to do number 4 because, oh my God, there's radicals.
Okay, let's see.
And number 6.
And number 6. Okay, any others?
No, but number 6 and number 5 are practically the same thing.
Yes. Number 6 and number 5 are going to be very similar.
Practically the same as 1.
What do you mean by 6 and 5 are the same thing?
'Cause look,
They're going to be very
x, y,
similar. They're kind of set up the same sort of way.
So I think we should just do 4 and 6.
Yeah.
Okay, so let's start with 6 and we'll save the ones with radicals at the to the very end because, radicals.
How are we able to assume which one's the biggest side? What if it's like disproportional?
Yeah, you just use your best eyeball at this point. Yeah, and that's honestly that's the only thing that I can say on these is because we don't know the measures. We have to go. This one looks like the smallest, and since they're drawn and they're supposed to be similar, the one that looks like is the smallest will be corresponding to the one that looks like is the smallest. All right, I'm gonna draw my setup here. Those are the ugliest triangles I think I've ever done. But they're all equally ugly, so that's okay. All right, gonna do the small side, small triangle. So there's the short side. I'm gonna call this one the medium side, and I'm gonna call this one the long side. Now the long side has to be across from the right angle, always. The other two are the ones that you've got a bit of flexibility on. That's going to be my short side. Now notice that there's a pattern to how the sides are, like there's a rotation pattern almost. You see? Little triangle fell over onto one of its sides. And then the other one is going to end up falling onto its hypotenuse. Okay, so you can use that as a pattern to help you decide which sides are corresponding. Because if you look at the small one, then rotate it to the right, chunk, and it falls over, chunk, and then kind of rotate this one again.
Could
Something.
we just draw it like that, like the way it's drawn there?
Here? Or here?
There, number 6. Because that's
Mhm.
what I did. I drew 1 and then I put the right angle. Because like, the baby one is the same up there. And then the,
Oh, you mean draw it in the same orientation as over here? Yeah, you can totally do that. Mhm.
it was a lot easier for me.
Sure, that's okay. Keeping them in the same orientation is what you see here. That's okay. Again, it's whatever helps you keep track of stuff. All right, so I'm gonna write my proportions. Let's see here. If I cover the hypotenuse of the baby triangle, I end up with y and a number. And if I cover the same side, the hypotenuse in my mama triangle, I end up with y and a number. So that will give me a proportion that will work. So I'm going to go ahead and solve for y first. I'm back into the easy realm of cross multiply and solve. And because I'm allowed decimals, square root of 8 is something between 3 and 2.
2.8.
2.8, okay. Okay, so there's 1. All right, I want x. If I look at my baby triangle,
X.
there's x and a number. There's no x's there, so that's not helpful. But there's x and a number. So I'm going to use baby bear and Papa Bear triangles. And I'm doing green over pink on this one. This ends up like geometric mean. You notice? Square root of 12 is a decimal rounded to 1 decimal place, the 10th place. Smaller than 4.
3.46.
3.46, so that gives us 3.5 because we went to the 10th decimal place.
I was just around that.
Mm-hmm, please. Yeah, round to the 10th decimal place.
X equals 3.5.
All right, now we're going to do z. Here's z. Okay, there's z and a number.
And there's Z.
There's z and a number, so I'm going to use Mama Bear and Papa Bear, and I'm going to do green over blue.
Okay, that's simple enough. You just see that.
Now notice how when I'm going from radical, the equal signs are straight, and when I go to decimal, I suddenly start making them all curvy. It's because the equals are, this is exactly what it equals, and the squiggly equals is más o menos approximately equal to. Okay?
Oh,
4.9?
4.9.
Can we box them both of them?
I'm sorry, one more time?
Can we box them both of them?
Oh, oops. No, you don't have to. This works. This one. Sorry. I got a little box happy. There we go. Let's use highlighter. There we go.
Four.
There it is. And that's it. That's all I had for you guys today. Oh, number 4. I'm sorry. You're right. Number 4. I'm so sorry. Can I scoot up to number 4? I got so excited. I was like, we got this, guys. All right. Set up again. I'm going to draw baby bear triangle, mama bear triangle.
Questions are really long. These questions are really long.
It's just the setup that takes a long time. And I'm especially because I'm taking a long time to do the setup, because on these the proportion is actually really easy to calculate.
Yeah.
It's just figuring out what side needs to go where that's the troublesome part. And so that's why I'm kind of slowing down and taking my time on this. Just color coding. All these radicals are intimidating. Okay. There's my setup. And now as I'm looking for things to solve, I really want to try to find fractions are going to be the easiest to deal with. Okay, if I look at this little one, I can make a fraction here, x over square root 3, which sounds intimidating. Or I can make a fraction x over 1, and that sounds so much easier. So I'm going to use this one. So as I'm looking through my triangle, I'm going to look for green and pink sides that gives me the most information and the fewest variables. This one.
Is x equals, square root of 3 on both of the the baby and mama bear triangles?
I'm sorry, I'm confused. Wait, why were they looking for the pink and the green and how did it last?
Because on this one, x over 1 is an easy fraction to think about.
Oh, okay.
As opposed to x over square root of 3. Yeah, so x over 1. So then x over this green over pink.
X over 1.
All right, x over 1 equals
X over
square root of 12 over square root 3. Okay, but remember we had a problem where we had a radical with a fraction inside of it and we rewrote it as a fraction made up of radicals? This one?
Ooh.
Remember this one? So anytime we have this, we can go to this. But that equal sign means that anytime I have this, I can go to that. If I were to rewrite the square root of 12 divided by the square root of 3 as the square root of 12 divided by 3, 12 divided by 3 is 4. And so that becomes the square root of 4. And what's the square root of 4? 2. This whole time I've been writing x over 1. Did I need to do that? I could just write, and so x equals, well, let's find y. Okay, looking at y, that doesn't have any y's. Square root. Square root. Okay, but look.
They're the same square root.
They're the same square root,
So
and there's no other variables.
we're good. 'Cause if
So,
we
you know,
equal
yeah,
that-
this one's going to be easier to deal with. So I'm going to do blue over pink.
Yes.
We could have done it the other way using this y plus 1, but it's going to create this really bizarre quadratic equation that then we have to like factor in. No, I just don't. No, I don't want to deal with it. Y equals square root of 3 times square root of 3. But anytime I have two radicals being multiplied together, I can rewrite it as one radical with those two radicands, the things inside, being multiplied together. And so what is 3 times 3?
9.
And that's the square root of 9. And what's the square root of 9?
3.
And we're done.
Okay.
And that's all I had for you today.